Welcome to 40+ years of wetland restoration in San Francisco Bay, lessons learned in future directions. I'm just going to start with a little bit of logistics. All of you attendees are muted, and you can communicate with us by typing questions into the questions box on your control panel. So you'll see a questions line. If you click on that, you can type questions into the box. So we look forward to your questions. And just so you know, the webinar slides and a recording will be posted to the website. So these webinars are being organized primarily for the benefit of the San Francisco Bay Restoration Authority's Advisory Committee members to ensure that they are as informed as possible on the current state of science and policy that impacts planning and implementing restoration projects in the Bay. And I would like to introduce today's speaker. Her name is Michelle Orr. She works for ESA. She is a water resources engineer and wetland restoration practitioner with over 20 years of experience in wetland restoration, planning, design, and integration of restoration with flood management. She has provided leadership and technical expertise to restorations in California, Oregon, Washington, Louisiana, and Florida, with a particular emphasis on tidal wetlands of the San Francisco estuary. And she led the environmental and engineering services for the South Bay salt pond restoration and other restorations totaling 27,000 acres. And you may have actually seen her on TV. She was the wetland scientist spokesperson for Measure AA. So without further ado, I am going to hand it over to Michelle.
Thanks, Jessica. It's great to be here today and to share the story of wetland restoration in San Francisco Bay and how those restoration approaches have changed over time, and talk about the current and emerging issues. I figured out when I was putting this talk together that I've worked on about 40 San Francisco Bay wetland restorations over the past 20 years, so this was a fun opportunity for me to weave my own experience into this overview, and I'll give some examples from the projects that I've worked on. And it's not advancing. All right, okay, back with you here. I just want to acknowledge my longtime colleague in wetland restoration, Dr. Philip Williams, who's a pioneer in the field, as well as many others. I'm telling the history of San Francisco Bay restoration is a big story, so it literally has a cast of thousands. The basic problem statement is one I'm sure that many of you are familiar with. In San Francisco Bay, historically, we had almost 20,000 acres of wetlands ringing the bay, and over about 100 years, we managed to destroy 80% of them. In the North Bay, a lot of these former marshes were diked and used for agriculture. Some of the wetlands were filled for development, particularly in the Central Bay. And in Sassoon Marsh, many of the wetlands were converted to managed duck ponds. Then in the South Bay and along the Napa River, quite a few marshes were converted into salt evaporation ponds. And the pink areas that you see here on the graphic on the right are all former salt ponds or current salt ponds. Along with the loss of marsh came a lot of damage and decline in the wildlife that live in the marsh and the fish that also rely on the marsh, including these special status species shown here, the endangered Ridgeway Rail and the endangered salt marsh harvest mouse. Fortunately, in about the 1960s, the value of wetlands became recognized, and mostly through the McAteer-Petras Act and the Clean Water Act, destruction of wetlands in San Francisco Bay was halted. The McAteer-Petras Act created BCDC, the Bay Conservation and Development Commission, which was the first coastal management agency in the nation. So San Francisco Bay really led the nation in requiring no net loss of wetlands. In the 1960s, the emphasis was really just on preserving what wetlands were left because there wasn't a lot of hope about bringing back what had already been lost. I'll talk about 3 eras of wetland restoration. These are approximate categories, but I think they provide a nice framework for talking about the history of restoration. The first era is what I call the first generation, which started in the 1970s. And restorations in this era were primarily compensatory mitigation projects paid for by developers to compensate for loss of non-tidal wetlands elsewhere. In the first generation projects, the design approach was to try to replicate the form of mature natural marshes. There were still a few left in the Bay Area, such as China Camp, shown here up in the North Bay. China Camp was formed through thousands of years of tidal flows and sediment deposition, and is one of the few remaining relatively undisturbed marshes in the Bay. It is not advancing. Okay, I just clicked on it. Go ahead, okay? Sorry. And typically in first generation projects, the primary consideration for was establishing the right conditions for plants to establish. So that was getting the right elevations, because elevations are key for determining the amount of tidal inundation, which in turn affects soil conditions for plant growth. So to create the target elevations, restoration sites that were too low were filled, often with dredge material, and upland sites that were too high were excavated down. And I'll give one example of a first generation marsh. This is the Mazi Marsh in Corte Madera. Mazi Marsh was historically tidal marsh. It was later diked off from the tides, and it was subsided a couple feet lower than a natural marsh. It was purchased by the Golden Gate Bridge District as mitigation for development of the Larkspur Landing Ferry Terminal, which would be just off this photograph here at the top of the photograph. For the Mazi Marsh restoration, the site was filled with dredge material to mature marsh elevations. And that fill area is outlined here in that orange outline that you see. There were a few channels cut, not very many, and then it was breached in 1976, reintroducing the tides. And what was observed after restoration was that the plants didn't thrive, and the back of the marsh didn't drain well. And so in 1980, the Bridge District went back in and cut some additional channels to improve the drainage. This helped, though the newly excavated channels quickly filled with sediment and became much narrower because there wasn't enough tidal flow to maintain these larger channels. So while the Mazi Marsh restoration and others like it could be successful in creating a vegetated marsh plain, the habitat generally lacked physical and biological diversity. So for example, here the site had few relatively straight channels with little branching, few plant species. And channels are really important for the exchange of water, sediments, nutrients, plants and animals between the marsh and the bay. And they're also used directly for habitat and foraging for some important species. Other first generation restorations relied on plantings to create, if you will, instant wetlands. But without the right physical conditions, often the plantings failed, though vegetation would eventually come in through natural recruitment, seeds and vegetation fragments coming in from the bay, getting deposited and establishing. In the early 1980s, it was recognized that plantings of common marsh plants wasn't needed because of the large seed source in San Francisco Bay. Now I'll move to the second generation. It's not moving again. There we go. By the 1990s, restoration practitioners had nearly 2 decades of first-generation restorations they'd had the opportunity to observe, monitor, and learn from. And so this second era of restoration in the 1990s and the 2000s is often referred to as a second generation. Also in the 1990s, resource management agencies began undertaking pure tidal wetland restoration projects, so not for mitigation. In the second generation, mature marshes like China Camp were still used as reference sites for long-term restored conditions, but now there were many recently restored younger marshes that can be used as case studies to help practitioners better understand how these younger marshes restored and evolved over time. So I'm showing again a photograph of Mazi Marsh, but this time I want to focus on the eastern side of it, the right-hand side of the image here. Like before, the dashed line is where the dredge material was placed. East of that dashed line was not filled, and both sides were breached in 1976. The eastern side started about 3 feet lower, and so it needed time to accumulate sediment through natural estuarine deposition. It took about 9 years longer to become vegetated compared to the western side. It took longer to evolve, but in the end, the habitat, and in particular, the channel complexity is much greater than the west side that had been filled, and you can see that on this image here. And ringing the bay, there were several more subsided breach sites like that eastern part of Mazi Marsh, many of them accidents rather than planned restoration projects. So by studying these marshes, practitioners developed a conceptual model of how they evolve over time from mudflat up to marsh. This graphic shows that evolution. It shows a young marsh up at the top that's relatively has low elevations. Over time, the daily tides bring in and deposit sediments, building up the mudflats. The tides also bring in the vegetation fragments and seed sources, as I mentioned, and once the mudflats are high enough, vegetation will establish and persist. At the same time, the tides scour the channels, and ultimately you get a mature marsh at about a high tide level and a complex branched channel system, which is shown there at the lowest image. So for this second generation of wetland restoration, the approach was to create an appropriate young marsh template and then let nature do the rest of the work in terms of developing it into a mature marsh and restoring ecological functions. So this era of projects relied on understanding and anticipating natural processes. The Sonoma Baylands restoration project was one of the first to use this second generation approach. The Coastal Conservancy of the Army Corps and the Army Corps led this project, and Sonoma Land Trust is the landowner. The project was implemented in 1996. This site was a former wetland that had been farmed for many years, and through diking and draining for farming, about 5 or 6 feet of subsidence occurred. The dredged material from the Port of Oakland was used to fill the site, but based on the conceptual model that I just showed, the site was purposely underfilled to about 1 to 2 feet below a natural marsh plain elevation to promote tidal channel development. And this image shows an early tidal channel beginning to form on the newly placed dredged material shortly after breaching. And this next image here on the upper right, there's a similar image of an early channel showing it's slightly more definition than the last picture I showed you. And the lower left is what the channels look like today. So there's a vegetated marsh platform with a sinuous tidal channel, steep sides like you would see in a natural marsh. And analysis conducted by ESA indicates that the length of channels, densities, and the patterns of the restored channels at Sonoma Baylands compare very well with these same metrics for natural marshes in San Francisco Bay. tidal channels are popular with the endangered Ridgeway Rails, who forage along the edge of the channel mud flat, and they find cover in the adjacent vegetation. They also are known to nest along the higher channel banks. And this Ridgeway Rail in the picture seems happy with the results. And that's a river otter in the foreground. This photograph was taken during the year 8 monitoring for the site in 2004. And actually, just earlier this year, the U.S. Fish and Wildlife, in their regular bird surveys for the North Bay, found that there are 20 rails using the site. Another substantial change for restoration planning has been a shift from the early focus on site-by-site restoration to consideration of regional restoration goals and opportunities. And a real milestone in this regard was development of the Habitat Goulds Project in 1999. This project brought together numerous agencies and over 100 scientists to consider the importance of restoration issues for a broad range of wetland organisms, plants, invertebrates, fish, birds, mammals, and also physical processes such as hydrology and sedimentation. The Goulds Project developed a regional goal of 100,000 acres of natural and restored baylands for species recovery and ecological health. This is approximately half of the historic wetlands acreage. And at the time the Goulds Project report was written, there were about 40,000 acres of wetlands in the bay, that middle graphic there. And so this goal represented an increase of 60,000 acres to meet that target. The Goulds Project also created maps of restoration priorities that have been guiding planning. In addition to the broader regional scope for restoration planning, the planning effort shifted from the early, relatively small projects to much larger ones. And this is a slide that I actually took from a presentation that Amy Hutzel from the Coastal Conservancy gave in 2007. And it was listing all the big projects that were coming up or were in planning. And I remember when Sonoma Baylands was breached in 1996, was the beginning of my career. It was one of the largest to date at 300 acres, and Al Gore was actually at the ribbon cutting. Then later that year, the Hamilton Wetlands restoration came online for planning at 900 acres, which was very large. And then this was quickly overtaken in terms of number of acres by planning for the Bear Island restoration in the South Bay, 1,600 acres. And I remember Clyde Morris, the Don Edwards National Wildlife Refuge Manager, and also the Bear Island Project Manager, telling me at the time that he had transferred jobs between federal agencies specifically because he wanted to work on this project, the largest and most significant in San Francisco Bay. Then came the Napa-Sonoma Marsh restoration planning for 10,000 acres in the North Bay. And of course, the South Bay Salt Pond Restoration Project at 15,100 acres, which began planning in 2003. And in case you're curious, Clyde Morris, that manager, did work on that project. So all of this leapfrogging in terms of project size occurred over a period of 7 years. I'll talk a little bit about the South Bay Salt Pond Restoration. It's located in the heart of Silicon Valley, woven in among the campuses of Facebook, Google, and many of the other high-tech companies. It's the largest wetland restoration on the west coast of the U.S. and really one of the most significant projects nationally as well. It's former tidal wetlands that were diked to create a series of salt production ponds. And Cargill sold this land to California Department of Fish and Wildlife and the U.S. Fish and Wildlife Service in 2003. The restoration projects being led by those two agencies plus the California Coastal Conservancy, Santa Clara Valley Water District, USGS, and the Army Corps of Engineers. And this project really exemplifies some of the benefits and issues associated with larger restorations. So with the size of the site is the opportunity for creating large connected habitats that are connected to each other and also to adjacent existing preserved habitats. And it's the opportunity to recover entire subpopulations of endangered species, which is really exciting. And habitat diversity was a key planning issue. The proposal was not just about restoring tidal marsh, but also upland ecotone and buffers, restoring creek channels and floodplains, and creating extensive managed ponds for shorebird and waterfowl foraging and nesting. Regional sediment supply was another big planning issue. The restored tidal wetlands are subsided and will create a large demand for sediment. So an understanding of the regional sediment dynamics was important for understanding potential impacts to the bay and to the mudflats in the South Bay, which provide valuable shorebird habitat. And like most large projects, the South Bay project has its share of complex issues. So there was the issue of water quality and potentially, especially the potential to increase bioavailability of mercury flushed downstream into the project area from the closed New Almaden mine. There's also the need to build in flood mitigation and new flood protection levees. And many other issues that come with the project that covers a large area. And this brings us to today's era, beginning in about 2010, and referred to here as the Baylands Ecosystem Goals Update era. So it's marked by restoration approaches expanding to address additional issues and benefits. So in 2015, the Goulds Project, which I was talking about, originally done in 1999, it was updated to reflect advances in wetland science and in particular to address updates to restoration approaches in light of higher projected rates of sea level rise. And with accelerated sea level rise, tidal wetlands will need more sediment than ever to keep pace with that rise. Elevations can be raised either through many decades of estuarine sedimentation or through fill with dredged materials, such as was done at Sonoma Baylands. And in this picture, this is dredged material being added to the Hamilton wetlands prior to breaching. And while sediment in the waters of the bay used to be abundant, that supply has decreased significantly. The decrease happened in about 1999. This graph is from David Schulhammer's work. That decrease became apparent as statistically significant a few years later, and this work was actually published in 2011. And it shows that step decrease in suspended sediment concentrations. This is for data at Point San Pablo. So what can we do? I'll provide the Lower Walnut Creek Restoration Project as an example of an approach to sediment and elevation management in line with the updated Goulds Project. This project is being led by the Contra Costa Flood Control District, and it's located along the lower 4 miles of Walnut Creek and its tributary Pacheco Creek. The project is about 2 or 3 miles east of the city of Martinez, and it's located in the brackish part of the estuary, fronting Sassoon Bay. And the site's in a really good location for sediment supply since it fringes Walnut Creek, which has a relatively high sediment supply compared to other creeks that flow into San Francisco Bay. The project is designed to maximize sediment delivery to the restored areas by connecting channels directly to the creek. And you can see those connections here, at least schematically, in this drawing with the little blue lines from the creek to the restored areas. And this is another way of looking at that same information. You see the creek going up the watershed there. There's your watershed connection, and then all those direct connections to the restored area from the creek. In addition, there are areas of high elevation already at the site where dredge material was placed previously, and in this figure, it's up in the northern part of this graphic. So the plan calls for grading down some of those areas to marsh elevations, but keeping many of them high to provide areas for the marsh to move upslope with sea level rise. So we talk about this as maintaining elevational capital. This time series shows the projected habitats of Lower Walnut Creek for existing sea level on the left, and then with 2 feet and 5 feet of sea level rise. Looking at the northern part of the map, you can see the marsh in green is gradually moving upslope. And even with 5 feet of sea level rise, parts of the northern project area remain transitional and upland habitats. So it's an island refuge. The project will create gentle slopes between the marsh and the adjacent ecotone and upland areas. The ecotone is valuable for its plant diversity and as a refuge from high tides and elevated storm waters for birds and terrestrial wildlife that use the marsh. It's also a place where there are dynamic interactions between the marsh and the uplands that create species and structural diversity. As sea level rises, these habitats are projected to get more deeply inundated, but they will move on their own naturally upslope. Rush Ranch is shown in the photograph here. Rush Ranch is in northern Sassoon Marsh. It provides a natural reference for this type of habitat for a brackish marsh environment. Marsh ecotone transitions are one of a suite of habitats that make up what's referred to in the Goulds Project update as a quote, complete tidal wetland system. The Goulds Project recommends creating a wide range of habitats along a gradient from subtidal to upland habitats, and this graphic is showing an idealized version of that gradient of habitats with eelgrass and oysters in the shallow areas transitioning through intertidal mudflats and marsh into the uplands. And this range of habitats can be very valuable because they provide different habitats for different species at different points in time. This focus and emphasis on the complete tidal wetland is a shift from this single species orientation of some of the earlier work, which was more focused on a healthy marsh plain and channels. And here are a few examples of marsh to upland transition habitats. Alkali meadow provides a high plant species diversity and can actually be rapidly created through rapid establishment of rhizomatous native plants. Seasonal wetlands are shown in the top right. They provide forage habitat for shorebirds and waterfowl. High marsh ponds and playa habitat are shown in the bottom right. And all of these photographs were taken at Rush Ranch as well. And here's an example of a tidal pond and seasonal wetland complex that was recently restored at the Hamilton restoration in Novato. The ponds create habitat diversity, and each pond is actually stepped, so each pond is slightly higher than the next as you move from the bay to the landward side. So this provides a continuum from lower to higher, and as sea level rises, the lowest ponds will become more tidal, but the functions of those ponds can shift upslope. And the tidal part of Hamilton you can see in the distance on this graphic with the bay in the background. So moving to the tidal areas, Hamilton is a great example of the benefits that these wetlands and sheltered intertidal mudflats can provide for aquatic species. Tidal wetlands in other estuaries are recognized as providing important fisheries nurseries and increasing primary productivity, and there is increasing awareness in San Francisco Bay of these contributions. A lot of what happens underwater is a little hard. It's not as visible as some of the other parts of restoration. So I wanted to show some photographs here of the year 1 and year 2 fisheries monitoring at Hamilton. I will say that the site's expected to evolve into tidal marsh in the long term, but the site is currently tidal marsh, a combination of tidal marsh and sheltered intertidal and shallow water habitat. So in these photos, you see multiple age classes for a broad range of mostly native fishes. So I picked out some photographs here, striped bass and Pacific herring you can see, along with a rock crab and native Olympia oysters. The site's providing nursery habitat as well as food for adult fish. The largest predators, such as the adult bat ray and the leopard shark that are shown here, are found just inside the site, closest to the breach, closest to the bay. And continuing bayward on this complete tidal wetland gradient, this is another project, the Living Shorelines project, that is restoring in the shallows of the bay. This project is restoring oysters and eelgrass. The photographs here are from the project implemented 5 years ago up in San Rafael on land owned by the Nature Conservancy, and this project is being led by the Coastal Conservancy and lead scientists from Romberg Tiburon Center and a number of other partners listed there. This project has added significantly to the ecological diversity of the bay, and it's really helping bring to public awareness the value of the shallows and these offshore habitats as well. So looking forward, the San Francisco Bay Area is on its way to meeting the 100,000 acre restoration goal, restoring up to half the historic baylands that have been lost. The Bay Area has a rich history of restoration, and as you've seen, a history of learning from that restoration. And critical to this learning curve has been monitoring of prior restorations and reference sites, and then applying lessons learned from those sites to the next sites that are being planned and designed. And continuation of this learning curve will be important to meeting this target successfully. Reaching this 100,000 acres will also require a sufficient level of funding. And of note, almost exactly a year ago, Measure AA was passed to support these types of projects. It's been called a once-in-a-generation opportunity to fund tidal wetland restoration, and also it will fund associated public access and flood protection that's needed. And for those who aren't familiar, Measure AA is a $12 per year parcel tax that will raise $500 million over 20 years for these types of projects. It was passed by a 70% margin in the 9-county Bay Area, and those funds are being administered by the San Francisco Bay Restoration Authority, who is the host of this webinar. If you're interested in knowing more on this topic, there are lots of great resources out there. I've listed a few of them here, and I understand that this information, this slide will be available through the link to the webinar series, so you can take a look there. And at this point, I will just ask if there are any questions.
Great, thank you, Michelle. So as I mentioned earlier, you can type your questions into the question box on your control panel. So while we're waiting to get questions, I will just ask a question. Could you tell us a little bit more about the sediment issue. We hear there's a sediment deficit. How are we going to deal with that? Why is it so important, etc.?
Right. Yeah, I provided a few examples of projects that use dredged materials. Actually, these examples might be a little heavy on the dredged material because not all projects do reuse dredged material. That's one way of trying to get sediments into these sites. I'd say there is a general acknowledgement that it's really important to keep the sediments that we have in the bay and that get dredged from our marinas and from our shipping channels, to keep that sediment in the system and beneficially reuse it for this type of restoration work. That said, it's complicated, and there are a number of policy issues and economic issues that have prevented that from occurring more than it already has to date, but that's something that a number of agencies are working on, trying to figure out how they can make that happen more easily and less expensively. There's also upland material as a source of fill. At Bear Island, one of the 3 parts of that restoration actually became a upland dirt disposal area, if you will, where when there were grading projects happening in the area that had excess material they were generating, they could take it to Bear Island and place it. And there was a plan for where it would go so that it could provide ecological benefits once the site was breached, and all that material was delivered free of charge to the project. I know the South Bay Salt Ponds project would like to get their projects lined up, permitted, and ready to go so that they can be ready to receive those same sources of fill, which has been really effective. There has been a set a match effort where dredgers who have material can get matched up with restoration sites that need it, and I understand there have been a few matches that have been made, or at least initiated through that. So really, I'd say right now, all options are being explored, because we do know that there's a need, with all the subsided areas that are available for restoration, there's a need for elevation, and then particularly with sea level rise, that even just increases that need for elevation and sediment.
Okay, great. Well, we've got a couple questions that have come in. So I will start with, how are restoration strategies evolving to consider movement of species, including invasives, with climate change?
That's a really fantastic question, and it actually is a big issue that is being discussed in the current Balance Goals update. Probably the most progress on that has been with managing invasive plants through the Invasive Spartina project. As many of you may be aware, there's an East Coast version of Spartina that was introduced to our estuary. In the first generation, the grade and plant generation of restoration, it grows really well, which is why it was selected. However, unfortunately, it is not good for our ecosystem here. And it also hybridizes with our native form of marsh grass. So it's been difficult to control, and the Invasive Spartina project has really made fantastic progress over the past probably 10, 15 years in managing Spartina to keep that really limited in the system. Some other invasive species are more problematic and harder to manage, like Asian clams and Sassoon marsh, that are eating a lot of the food that gets produced at the base of the food chain. I am actually an engineer, so I'm going to refer you to the Goulds Project update for more information on that.
Okay, we have another question. What caused that step change in bay water sediment load as measured at Point San Pablo?
Yeah, so let me back up a moment and just talk about the history of sediment in the bay. According to our best estimates of what may have been the amount of sediment in the water column before humans came in and made big changes, we think we may be at about that level now. But what happened is that in between, a whole slug of sediment came into our system from hydraulic mining in the Sierra. So this is basically pointing a hose of water at a hillside to ferret out the gold. And so that just washed huge amounts of sediment into our system, and it made the system very, very muddy for many, many years. And I'd say the bay was actually the beneficiary of that. And what we've seen is that pulse of sediment has now worked its way through the system. And those levels are going back down. And what David Schulhammer hypothesizes in his paper there is that we went from having mudflats with very large supplies of sediment stored in the mudflat, where the limiting factor of getting that mud into the into other areas was really just you needed to wait on processes for the waves to whip up those sediments into the water column and the tides to carry them around. The hypothesis is that actually we reached kind of the bottom of that storage, and the mudflats got low enough that those same processes were no longer carrying mud into the water column. So the whole system became, it transitioned from transport limited to supply limited.
Okay, interesting. So you sort of touched on this already, but do we have enough sediment for restoration from dredging harbors? And if not, do we have other sources? You mentioned the upland sources, but I think we have at least one other source I can think of. The navigation channel to the harbors. Right.
Generally from dredging, I don't know the mass balance on this. My thought is we probably need more, but we certainly need all the dredging materials that we could get.
And then, of course, the creeks can bring
to
the bay as well.
And part of it is that sediment, fine sediments have been seen as a problem in creeks, and there's been a lot of effort to make sure those aren't generated and they get trapped in detention basins up in the watershed. But when you move down further, down the creek to the bay, you actually want that sediment to make its way through. So there's a growing recognition that what may work in one part of the system may not be causing some impacts in another part of the system, and we'd like to have that transport of sediments from the watershed through the creeks all the way to the bay.
Okay. Any other thoughts about how the strategies have changed over time, what the future directions? You've mentioned sediment adaptation to sea level rise, there's the invasive issue. Any other hot issues we should all be more aware of?
You know what I'll do is I can just remind people of some of the resources that are available if you're interested in knowing more. In particular, if you've got 10-15 minutes, Letitia Grenier gives a short talk there, and I provided the link to it. It's a very easy, entertaining way to get a bit up to speed on what some of the current issues are.
Okay, and now we have one more question. Since much restoration now involves importing large volumes of soil or sediment, have you seen any impacts from contamination within the imported volumes?
The imported sediment that gets placed into wetlands is screened very carefully for contaminants. There are a number of contaminants that can be present in these dredged materials, particularly if they are from shipping channels and of a certain era in particular. And so the California, the Regional Water Quality Control Board has direction, guidance on contaminant levels that are acceptable for placement in wetland environments. There are two criteria, actually one criteria for sediments that are buried deeply, and then more stringent criteria for sediments that sit on the surface of a wetland. And by surface, I mean 3 feet, so it's a pretty deep cover layer. To some extent, contaminated sediments can be a limitation on what gets accepted by a site.
Oh, maybe you can talk about, I think there's an example of a site that accepted the contaminated.
The Montezuma.
Yeah.
The Montezuma wetlands in Sassoon Marsh is actually a very large site that is taking millions and millions of cubic yards of dredged material, and the dredgers pay to actually place it in there. And they, like Bear Island, they have their grading plan ready, and they tell people where to place the material, and once they have enough material filled in a certain area, they can then breach and then reestablish wetlands there.
And so they were able to bury some of those sediments deeply enough so that it was okay to put them there.
They did, yeah.
Okay, we have another question. How has monitoring changed or been refined over the course of the past 40 years? Any suggestions on how to improve the efficiency or efficacy of monitoring in future projects?
That is a great question. And really, monitoring is so important, and I know it's often hard for agencies to get funding for monitoring, and it is important that it's done efficiently. But it's through that monitoring that we really learn what works and what doesn't, and we learn about any surprises that come up that we didn't expect. Sometimes bad surprises, but sometimes really good surprises, and you find you want to be doing more of something. How it's changed? Well, over the last 40 years, I'd say the first generation of projects were really not monitored. So that is a big change in that now there are requirements for monitoring. Those first generation of projects, they didn't have clear performance criteria or goals for the project. They didn't have monitoring, and they may have had some simple goals, but when you went through and compared the goals to how the project appeared to do, first of all, you had to do it without monitoring data, but just on the face of it, a lot of them didn't even meet their goals. And so then in the second generation, the criteria became more stringent and monitoring got added. The use of remote sensing has really changed the way monitoring's been done. The use of really affordable aerial photography, repeat aerial photography, you can tell a lot through that. And then also now the use of drones is on the cutting edge for really high resolution photography, bathymetry. You can use it for habitat wetlands mapping. So I'd say those are the some of the things that have provided a data richness at a pretty affordable cost these days with monitoring.
Oh, and just getting back to that impacts of contamination relating to that, to monitoring, I think there also have been some advances in like monitoring fish on sites to see whether they're uptaking contamination and things like that. So maybe that's one of the advances. It's not just whether the contaminant is in the sediment, but it's how does it get into the food chain. That seems to be one of the advances that I have heard about.
There's also environmental DNA that's being used where you can take a water sample and it has a little history in that water sample of what fish may have been in that area. And so this is an emerging technology. It's being used in the Delta on a pilot basis, and shows some promise for being able to say more about fish use of these areas without having to go out and actually haul trawl nets and do very labor-intensive fisheries monitoring. I think part of the reason why there's not as much known about the fisheries use of these tidal wetlands is because they're technically very challenging to monitor. I know from working in the Delta, at least, a lot of the monitoring data for fish was in the major channels, the big channels, the Sacramento River, the San Joaquin, and almost zero information in some of the small tidal channels and in the wetlands. And that was simply because it was really hard to take a boat in there. And so there was a prioritization of where people put effort. So some of these new emerging technologies might make it easier to get this type of information.
And I think birds are another thing that people tend to really care about as far as the monitoring, like the birds' use of the sites, and then also whether their eggs are being affected by any contaminants and things like that.
That's true, yes.
We had another question going back to the dredged sediment reuse, asking whether the U.S. Fish and Wildlife Service has requirements for that. And I think this question came up when we had our first webinar on water quality in wetlands, and we did get some information from U.S. Fish and Wildlife Service about how they're handling this issue, and we can provide that. I don't have a specific answer to that question. I don't know if you are familiar with that. It's more the water board.
Yeah, I know the State Water Board and the EPA, yes, are often involved in looking at dredged material quality from a chemical perspective, and I'm not familiar with Fish and Wildlife procedures there.
Okay. Well, we have a couple more minutes, and I don't see any more questions. But if there's any concluding remarks you'd like to make, you can.
I suggest we finish a few minutes early.
Okay, great. Well, this has been a very enlightening discussion, and I thank Michelle for being here and sharing her knowledge, and as well as thank everybody who has tuned in and asked questions and listened, and hopefully you are intrigued and will follow up on her suggestions for where to get more information. And with that, we will wrap up the webinar. Thanks very much.